Hi, I'm Fernando Pereira from UFMG, and today we shall talk about local register allocation. That's the version of the register allocation problem that happens in the context of a single basic block. Let's start this class explaining what is register allocation. A program needs locations for the variables that it manipulates. These variables can be stored in either the main memory or in registers. Memory is plenty, but it's slow. Registers are few, but they are fast. So ideally, the variables that are used the most should be in registers. Variables that are seldom used can remain in memory. They will be fetched to registers whenever necessary. And with this, we have that register allocation is the problem of mapping variables in registers, in a way to have the most used variables in registers most of the time. Register allocation is a problem that begs many questions. I'm leaving a few to you here in case you want to stop the video and take a look into them to think about. And for an example, consider this program. It doesn't matter what it does, we just need the code. That's the assembly code in x86. In this case, all the variables are mapped in memory. And here in the middle, we have the code of the same program, but this time with variables mapped onto registers. The program is shorter and it's much faster, not only because it has less instructions, but also because it does not access memory as much. By the way, why do we talk about register allocation but we do not talk about memory allocation? Well, basically because we can, for all the purposes, imagine that memory is infinite. Of course, that's not true, but we can assume it, just for the sake of simplicity. And can you think about a good algorithm to map variables to registers within a basic block? Here is it. The code's not that short, but don't worry, we will take a look into the whole thing in more details. However, if you would like to read the code before we move on, I'm leaving some questions to you here, so that you can think about the algorithm before we talk more about it. You can stop the video and take a look into the code and the questions. In a nutshell, the algorithm traverses the instructions in the basic block. Then, for each instruction, it liberates the registers used by the operand, if these operands have no further use in the future. In this case, we say that the operand is dead at that point. And then, the algorithm allocates registers for the variables defined by the instruction. We shall assume that every instruction defines just one variable for simplicity. Of course, there is more to it. For instance, let's consider what we do about the operands of the instruction. These operands are, for instance, variables u1 and u2 in this instruction above the figure. The first thing to consider is that if some of these operands are mapped onto memory, we will need to load them in registers. And then we liberate the registers that are currently allocated to dead uses. And when we consider the variables defined in the instruction, and here again I'm assuming that each instruction defines just one variable, we still need to find a good register for that variable. Finding this register is not so trivial, because maybe all the registers are already taken. Then what do we do? In this case, we need to map some variables to memory. This act of mapping variables to memory has a name. It's called spilling. Typically, when choosing a variable to spill, we choose the one with the furthest use. In other words, we spill the variable that will be used the farthest in the future. This is a heuristic. It tends to minimize the number of spills. But minimizing the number of spills is actually an NP-complete problem. So usually compilers, they will resort to some kind of heuristic approach. By the way, once we spill a variable, we need to map it to memory. We do it by choosing a memory address for the spilled version of that variable. And we use a store operation to copy that value to memory. Coming back to this heuristic of spilling the furthest use, this is something that was invented actually in the context of operating systems. That was a heuristic used to evict virtual memory pages. It's due to an IBM professional called Belady. So this is called the Belady's heuristic, or the Belady's algorithm. And by the way, remember that we are doing register allocation within a basic block. Even if a variable is not used within the basic block, that does not mean that the variable is dead. Indeed, it can be used in other basic blocks that follow this one that we are considering. Let me show how the local register allocation algorithm works with this simple program. We can represent the live range of the variables as bars. In this way, doing register allocation means to store the variables into bins. Here I'm representing the bit width of the variables as little blocks. But width is not really important for register allocation, at least in the context of this class. We can simply assume that all the variables fit into the available registers. Let's, in this example, assume an architecture with two registers only. I will call them R0 and R1. They are large enough to fit the values of any of the variables in our example. We start by finding a location for variable A. We have two free registers. We can store A in either one. Let's place A onto R0. Now we need to place B somewhere. We still have one free register, that's R1. We place B onto R1 in this case. We now need to place C somewhere, and that brings in a problem. All the registers are taken. We will have to move one of the variables to memory. But which one? Would you like to think about it? We end up spilling A because it has the farthest use. A will only be used at the end of the program. B, on the other hand, is used much before that. And to perform this mapping, we insert a store instruction for variable A. We next allocate D. Notice that we can place D and B in the same register because R1 is freed from B before we define D. To allocate E, we proceed in the same way we did to allocate D. E can exist in the same register as C because C dies at the instruction that defines Z. Upon implementing our second to last instruction, we free R0 and R1 because these variables have no further uses. And to process the last instruction, we load A from M1 onto some register. Either R0 or R1 would do. Because they are both free, let's just pick up R1. Notice that the same variable can coexist into multiple locations and that the variable does not have to be always in the same register. In this example, A started in R0, then we copied it in memory and in the address N0, and then we recopied it into a new register, which is R1. Notice that the problem of finding the minimum number of registers for a basic block has polynomial time solution actually. This problem is equivalent to coloring interval graphs, which is a problem with exact solution in polynomial time. In this case, we are assuming that all the registers have the same size. Otherwise, the problem would become NP-complete. I leave in a link to a paper here in case you want to know more about it. However, the problem of minimizing the number of loads and stores in the program, which we use to map variables to memory, is indeed an NP-complete problem. Again, there is a paper about that on the bottom of the figure. And with this last note, I end this part of the course. We had talked about control flow graphs, about direct, basically, graphs, pinhole optimizations, and now local register allocation. Some of the key papers about the subject are listed here. In the next class, we shall start talking about data flow analysis.